Hi, this is Tzvi Rosen with our next lecture in the Algebra and Geometry class. Today's topic will be quadratic equations and conic sections. This involves a little bit of a paradigm shift for us because up until now, our understanding of the connection between algebra and geometry was by understanding coordinates as algebraic numbers satisfying rational polynomials. Okay, so for instance, we knew that the intersection of a circle and a line had coordinates which satisfied equations with polynomial equations with rational coefficients. Okay, so this might have been, x minus h squared plus y minus k squared equals r squared, together with ax plus by plus c equals 0, and then you could solve and find two solutions, x1, y1, and x2, y2, and those would satisfy these two equations on the right. Okay, but now we're going to talk about equations defining curves and surfaces. In particular, we're looking at the set of all points. And you know what, I'll write this, type this. Set of all points satisfying some polynomial equation in n variables. Okay, and we're going to start with two variables working in the plane. And in general, these are called algebraic varieties. The set of all points where a set of polynomials vanish are called algebraic varieties. But in our context, we're just going to be talking about curves and surfaces. Okay, so let's start with the simplest possible polynomial equations defining an algebraic variety. And those are linear equations. So equations of the form ax plus by plus c equals 0. Okay? This is a general linear form. Okay, and it's general because we are allowing all possible terms that have degree 1 or degree 0. Okay, and this equation very simply defines a line, okay, in the way that we're used to seeing it. Okay, so we get a line here, here. Okay, in the case where, for example, if c equals 0, then we've got lines through, let me make clear that this is the coordinate axes. So if c equals 0, then you've got lines through the origin. Fatten up the origin a little bit. Okay, but if c is non-zero, you get lines elsewhere. Okay. So we understand the algebraic varieties defined by linear equations pretty well. So the next step up is quadratic equations. So these are equations of degree 2. Okay, and if we want to be as general as possible, taking all terms with degree 2 or 1 or 0, what we get is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay, so this is the most general quadratic equation of degree 2, including all terms of degree at most 2. Okay? So we saw that linear equations always describe a line. But what do quadratic equations describe? Okay. Let's see if we can answer that question over the course of this lecture. Do quadratic equations in general define? Okay. So we're going to work on that now. But before we do, we're going to remember some examples of shapes that satisfy a quadratic equation. Okay, so first up will be the ellipse. Let's get this in blue. Okay, and this satisfies equations of the form x squared over a squared plus y squared over b squared equals 1. And that describes an ellipse with axis along the x-axis. You've got the points a0, minus a0, and along the y-axis you get 0b and 0 minus b. Okay, and we often think of this as a stretched out circle. Okay, so that's one, and you can see this includes just terms of degree 2 or 0. Okay, next up will be the hyperbola. Okay, and this is the classic example is x squared over a squared minus y squared over b squared equals 1. Okay, so the key here is this minus sign. And here you get your points on the x-axis, just as with the ellipse, a0 and minus a0. But then, you get this curve that sweeps out with two different branches. The thing that the conic that's probably most familiar to us is the parabola. And a classic example of that is equations of the form y equals x squared. Okay. I think we can leave it at that. You can be a little more general, but this is the classic example. Okay, so this is y equals x squared. And this is also one of the classic conic sections. And we'll talk about why these are called conic sections, how we derive them a bit later on. Okay, and we also, in addition to those conic sections, we also have degenerate conic sections. And they earn the name of conic sections, but only on something of a technicality. So one example of that is, let's get this magenta. We've got a pair of lines. Okay. Well, we could also get a double line. And then you could include tentatively a point, depending how you want to define things. So pair of lines would look something like, and we could qualify this a bit by saying this could be intersecting lines or parallel lines. Okay. You know what, let's just leave them as intersecting. The parallel case is not super obvious from the picture, so let's leave it as just a pair of lines. Okay. So we could get something like, pair of lines, you get this fat line, or you could get a point, and these would be described by equations like ax plus by plus c times dx plus ey plus f equals 0. Okay, so you can see it's a degree 2 equation, but it's a product of two degree 1 equations. Then you could also just get ax plus by plus c squared, okay, equals 0. That's a single line appearing to degree 2. That's why we call it a double line. And for a point, how could you describe a point with a quadratic equation? Well, you could say something like x squared plus y squared equals 0. Because we know squares are always non-negative, that means that there's only that both of these points are forced to have degree 0, are forced to be equal to 0. So x equals 0 and y equals 0. But again, these are all kind of, as we said, degenerate conic sections. So they're not true quadratic equations like these guys are. Okay, so now that we've reviewed our conic sections, what we want to do is start thinking about that equation that we had above. Okay, so again, it was ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay, so we want to pay most attention right now to this part. This is the degree 2 part. Okay, and one way of writing this expression, this degree 2 polynomial, and it's of homogeneous degree 2, so there are no lower degree terms. One way of writing it is to say this is xy times a matrix A, b over 2, b over 2, c times xy. Okay, and if you do this matrix multiplication, you'll see that the result is ax squared plus bxy plus cy squared. Okay, so we would love to be able to get rid of this term, okay, because then we would have what's called a diagonal matrix. And there's a great useful fact from linear algebra that real symmetric matrices, let's give this blue, real symmetric matrices are orthogonally diagonalizable. That means that there's a matrix A is equal to U transpose times some diagonal matrix times U, and I'll put the transpose in a moment. Okay, so U transpose times a diagonal matrix times U. Okay, so this A, b over 2, b over 2c, that's a real symmetric matrix, assuming we're starting with real coefficients, which we are. So what that means for this, we'll have xy times U transpose times some diagonal matrix, okay, which we'll call A prime B prime, times U times xy equals our original quadratic form. Okay. But then instead of sticking with this original quadratic form where we have bxy, and which we want to get rid of, what we can do is just make a change of coordinates. So we can say, you know what, instead of using x and y like we were before, we're going to use x prime and y prime, which will be defined as u times xy. Okay. So whatever u is, it's just some orthogonal matrix, which you can think of as a rotation in the plane. So these are new coordinates. And in our new coordinates, ax squared plus bxy plus y plus cy squared is going to be equal to x prime y prime times D, a diagonal matrix, times x prime y prime, which means it'll be equal to something of the form a prime x prime squared plus b prime y prime squared. Again, all the primes are a little annoying, and I apologize, but we'll start dropping those primes in a second. Okay, so this is a way to use an orthogonal change of basis, basically rotating your axes to get rid of an annoying cross term, this bxy. Okay, so instead of having ax squared plus bxy plus cy squared, we make an orthogonal change of basis. Okay, and you can refresh your linear algebra remembering how to do those orthogonal changes of basis in the plane. In particular, where you have, so a b over 2 b over 2c will be equal to u transpose du, and then let this u define your new basis, x prime y prime equals u xy, and then renaming xy to be our x prime y prime, so drop the prime basically, and we get this equation. And now we'll replace all of our original coefficients with capitals because they've changed in the process of this change of basis. But now we have this very nice ax squared plus by squared plus cx plus dy plus e, which leaves out the xy term. Okay, great. So now we have this quadratic equation with just 2 degree 2 terms. So now we can start considering special cases. So if a equals 0 or b equals 0, what we have immediately is a parabola. Okay, so for example, if a equals 0, we get by squared plus cx plus dy plus e equals 0. Okay, which means that we have, okay, so if you have c equals 0, then that will end up being a pair of lines. But assume you have c not equal to 0. Then you can divide everything by c, and you get x equals negative b over cy squared plus, or rather minus d over cy minus e over c, which is a lovely equation for a horizontal parabola. Okay. And by very similar computation, this would lead us to something that looks like y equals negative a over d x squared plus, or rather, minus c over d minus e over d. Okay, and this would be our vertical parabola. Okay, so we've seen case 1 where a or b is 0 and c is not 0, and in this case we'll need to assume that d is not 0. We get a horizontal or vertical parabola. Okay, great. So that's one case. So now, assuming that a and b are not 0, what we can do is complete the square. Okay, so we can complete the square. We'll get ax squared plus cx, and then you can complete that square by taking, well, you can first divide through by a, so you get a times x squared plus c over ax. Okay, and then you can add on a plus c squared over 4a squared to complete that square, and then you'll have plus b times y squared plus d over b y plus d squared over 4b squared. Okay, and then plus some constant. Okay, so this will be our e prime equals 0. Okay, and then you can make another change in coordinates. So this time you're just translating. So instead of having x, we'll take x prime will be x translated by this c over 2a. Okay, so that this completed square is just our x prime squared. Okay, and then here similarly we'll translate our y to get y prime equals y plus d over 2b. And now we're left with this equation here after we drop the primes. Okay, so we've successfully gotten rid of two more terms, the degree 1 terms, and we're left with alpha x squared plus beta y squared plus gamma equals 0. Okay, things are looking even simpler. So now we should keep in mind we've already addressed a case of having parabolas, and in the case of c equals 0 or d equals 0, those would give you a pair of lines. But now we're on to a simpler form, alpha x squared plus beta y squared plus gamma equals 0. Okay, and now we can start getting really into the cases. So if we have gamma equals 0 and beta equals 0, or gamma equals 0 and alpha equals 0, we're going to find ourselves with a double line. Okay, so if gamma equals 0 and beta equals 0, we have alpha x squared equals 0. That just means we're looking at the line x equals 0 as a double line. Okay, similarly, if gamma equals 0 and alpha equals 0, then we have beta y squared equals 0, which means we're looking at the double line y equals 0. So this is double lines. Okay, well, how about if gamma equals 0 and the other two are non-zero? Well then, so you could have alpha x squared plus beta y squared equals 0, in which case you could be describing, if they're both positive or both negative, we could be describing a point. Okay, so both positive, we could be describing a point, right? Because the only thing that would satisfy that is if both x and y are 0. If they have different signs, then we're looking at a difference of squares, which we can factor. Okay, so that's root alpha x plus root beta y times root alpha x minus root beta y. And that's set equal to 0. So that gives you a pair of two different lines. Okay, so we're covering all of our degenerate conics. Okay. How about if alpha equals 0 or beta equals 0, but we know gamma is non-zero? So that means we have, for example, alpha x squared equals minus gamma. Okay, so assuming gamma is negative, so this is going to be two horizontal lines. X equals plus or minus square root of minus gamma over alpha. And similarly for beta y squared equals minus gamma. Okay, so this is also a pair of lines. Both of these. Okay, great. So that's covered all of the possible cases where we have zeros. And now we're assuming that all of these are non-zero. This should say alpha, beta, or gamma. Okay, so what we're left with, well, we can divide through by gamma and put it on the other side of the equation. So I guess we would be dividing through by minus gamma. But we're left with rx squared plus sy squared equals 1. Okay, so if both of these are negative, so then you have two negative numbers adding up to 1. This is going to be the empty set. No points can satisfy this. No real points satisfy this equation. Okay, how about if both are positive? Well, in that case, we should see that we're describing an ellipse. Okay, we have, if r is positive, you can write it as 1 over a squared. Let's just write that. R equals 1 over a squared. and s can be written as 1 over b squared. And that's exactly the equation for the ellipse that we wrote earlier. Okay, and then the other option is that they have different signs, right? So we saw both negative means the empty set, both positive means an ellipse, and if they're different, then we have, for example, if we let r equals 1 over a squared and s equals minus 1 over b squared, we have x squared over a squared minus y squared over b squared equals 1, which is a hyperbola. And from this one, if we get the exact opposite, minus 1 over a squared, s equals 1 over b squared, we're looking at y squared over b squared minus x squared over a squared equals 1. This gives you a vertical hyperbola, so you get something that looks like this. Okay, whereas this gives you something that looks like this. Okay. And this is a vertical hyperbola. Okay, so we've covered all of our cases, and we've seen that no matter what weird general quadratic equation we start with, we're going to end up with one of the conics or degenerate conics, or maybe a point or the empty set, depending on whether what you consider those. Now we'll show how to put a general quadratic equation in standard form on an explicit example. So here we have the equation x squared plus 6xy plus y squared plus 8x plus 3y minus 9 equals 0. Okay, so as we did in our discussion before, we start with the degree 2 part. Okay, so this can be re-expressed as x times xy times the real symmetric matrix, 1, 1, and then 3 goes on the off diagonal, and xy again. Okay, and then we're going to want to orthogonally diagonalize this. Okay, and there are calculators online that you can do this with if your linear algebra is rusty, but we'll do it explicitly. So the first thing we do is an eigenvalue computation. And we compute that by computing the determinant of this matrix minus lambda times the identity. Okay, and we get 1 minus lambda squared minus 9, which is 1 minus 2 lambda plus lambda squared minus 9, which is equal to lambda squared minus 2 lambda minus 8. Okay, so this is not hard to factor. 8 factors as 1 and 8, or 2 and 4. See that 2 and 4 works here, so we get lambda minus 4 times lambda plus 2. So our two eigenvalues are 4 and minus 2. Okay, so again, our matrix is 1, 3, 3, 1. So now we have to find the eigenvectors. So we have for lambda equals minus 2 and lambda equals 4. For lambda equals minus 2, the matrix would be 1 minus negative 2 is 3. So 3, 3, 3, 3 times v1, v2 equals 0. Well, then just v1 is equal to minus v2. So an example of an eigenvector corresponding to lambda equals minus 2 would be the vector 1, minus 1. As for lambda equals 4, the corresponding matrix A minus lambda I would be minus 1. Sorry, that should be minus 3. That makes more sense. 3, 3 minus 3. And in this case, an eigenvector would be v1 equals v2, so the vector 1, 1. Okay, we need this to be orthonormal, so we want to make sure that the dot product of each vector with itself is 1. So to do that, we just simply divide by the square root of its norm, which in both cases is 2. So our orthonormal basis is 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. Okay? So then our matrix 1, 3, 3, 1 is equal to, so we're going to have the transpose times the diagonal times the original basis for the eigenvectors. So we get, so again, it's 4 and minus 2, or rather minus 2 and 4 is the order we put it in. So we have minus 2 and 4 times 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2, and the original one. Okay, great. And so now we make our change of basis. So we're going to change to x equals 1 over root 2x plus 1 is minus 1 over root 2y. And y, this will be our x prime. Y prime is equal to 1 over root 2x plus 1 over root 2y. Okay? And now we've got to see how that affects our original equation. Well, we know what it does to the quadratic part. So now our quadratic part is minus 2x prime squared plus 4y prime squared. Okay. What does it do in terms of 8x and 3y? Well, we can use the transpose since that's the inverse. So it's going to take 8x and it's 8x plus 3y, and it's going to turn it into 8 over the square root of 2. So rather, let's get a new slide. For the linear part, we have 8x plus 3y. This is equal to 8, 3 times xy. And we know that xy is equal to u transpose times x prime y prime. So this is equal to 8, 3 times our transpose of the orthogonal matrix, of the change of basis matrix. So we get this times xy times x prime y prime, which gives us eight plus 3 over square root of 2 times 3 minus 8. So that's 11 over square root of 2. And minus 5 over the square root of 2 times x prime y prime, which gives us 11 over root 2 x prime minus 5 over root 2 y prime. Okay, so our new equation is minus 2 x prime squared plus 4 y prime squared plus 11 over root 2 x minus 5 over root 2y minus 9 equals 0. Okay, we've gotten rid of our xy term, though now the coefficients are a bit messier. Sorry, this should have been x prime and y prime. Okay, but we don't like x primes and y primes, so we're just going to drop all the primes. Minus 2x squared plus 4y squared plus 11 over root 2x minus 5 over root 2y minus 9 equals 0. Okay, and then we'll keep in mind that we have to change our basis when we're actually trying to represent the original hyperbola, the original conic. Pretend we don't know it's a hyperbola at this point. Okay, so now we can complete the square. So we have x squared, so we have minus 2 times x squared minus 11 over 2 root 2x plus 4 times y squared minus 5 over 4 root 2 y minus 9 equals 0. Okay, great. So this is minus 2x squared minus 11 over 2 root 2x. Okay, now we're completing the square, so we're going to get 11 over 4 root 2 squared. Okay, so we also want to subtract the same amount. Okay, and the same deal goes for y. So we have 4y squared minus 5 over 4 root 2 y plus half that squared, so it's 5 over 8 root 2 squared. And then we'll subtract the same. Okay, and still get minus 9 equals 0. Okay, so what do we have? We have x minus 11 over 4 root 2 squared times minus 2 okay, but then we have to also take into account plus 2 times 11 over 4 root 2 squared. Okay, and then the y term is plus 4 times y minus 5 over 8 root 2 squared. And we also have to subtract 4 times 5 over 8 root 2 squared. Oh, sorry, this should be a 5, not a 4. Okay, and subtract 9, and that's equal to 0. Okay, so we should group all of our constants. So we get, so minus 2, and this is going to be another x prime squared plus 4 y prime squared. And then the remaining constants are, so it's 2 times 121 over 8 times 2 over 16 times 2 is 32, minus 4 times 25 over 64 times 2 is 128, minus 9 equals 0. Okay, and then this constant should be minus 71 over 32. So we have minus 2x prime squared plus 4y prime squared minus 71 over 32 equals 0. We can move this to the other side and then normalize, and we'll get minus 64 over 71 x prime squared plus 32 times 4 is 128 over 71 y prime squared equals 1. Okay, so at this point we can see that what we're looking at is a hyperbola. And, again, we'll just get rid of these primes because primes are ugly. Okay, it's a hyperbola where the forms under so we know hyperbolas either have one of the two squares with a negative sign. In this case, it's the x squared. So we have y over b squared minus, should be y squared over b squared minus x squared over a squared equals 1. And here, b is the square root of 128 over 71, or rather, the square root of 71 over 128. And a is the square root of 71 over 64. And you can simplify this. This is root 71 over 8 root 2. And this is root 71 over 8. And those will give us the minor and major axes of the hyperbola. So geometrically, what we did through this process was, now we've arrived at this hyperbola, which looks something like this. Okay, but in the previous step, when we completed the square, we were changing to a hyperbola that would have been shifted up and to the right. Something like this. So this is the translation from completing the square. And the change of basis was a rotation of about 45 degrees, so we would get something that looks like that, roughly speaking, after rotating this object. Okay. So that was a long example, but hopefully it gives you the sense of what we were doing here. We make a change of basis, we translate, and then we have something in standard form. Possibly along the way, something turns to 0, and so we come to a degenerate conic or a parabola. Okay, so why are we specifically looking at conic sections? Why are they called conics? Why does degree 2 mean suddenly we're looking at a cone? Well, I think the best perspective is to think about what are the alternatives. The simplest equations in 3 variables, well, you could have something like x squared plus y squared equals 1, and that defines a cylinder. Or something like this. Okay. But if you try to cut a cylinder, you can get an ellipse. You can get a circle, clearly, which is just a specific example of an ellipse. You can also get 2 lines, but that's about it. You can't get hyperbolas, you can't get parabolas. Okay, so if you want to be a little bit more complicated of an equation, you can get x squared plus y squared plus z squared equals 1. So then we're looking at a sphere. Okay, pardon my poor drawing of a sphere. But there, the only section that you're going to get when you cut it is a circle. Okay, so only circles. Okay, so this gives us, and maybe a point if you're careful. Okay, and this gives us ellipses and pairs of lines. Okay. So really, just by adding in this minus sign, x squared plus y squared minus z squared equals 0, we get something slightly more complicated in its equation, but all of a sudden we get the ability to represent every single possible quadratic equation in two variables because when we sub in, when we intersect by a plane, so we get parabola here. Oops. Let's make this a bit wider. So this gives us parabola. And we also get an ellipse here. And we can get a hyperbola over here. Okay. And similarly, we can get all of the degenerate conics, pairs of lines, etc. Okay, so ellipses, hyperbolas, parabolas, and then degenerate conics. The key here to understand is we're making the substitution z equals ax plus by plus c. Okay, and so plugging that in, you get the full generality of equations, quadratic equations in two variables. Okay, and so that is the reason that we've been talking about conic sections, and we'll talk more about their geometry and about some of the cool constructions that you can do to understand their geometry, in particular the Dandelin spheres, in the next lecture. Thanks.